So before the break, guys, we defined two types of energy: potential energy, which in the context of gravitational potential was mgh; kinetic energy, the energy of movement, 1/2 mv squared. And then the day before we left for our week and a half long break, we talked about the concept of work. We defined work as the change in energy. Therefore, work, we could say, is delta E. We call that the work energy theorem, by the way. The work energy theorem says work is equal to delta E, final energy minus the initial energy. We also said it depends upon two things. Why does it depend upon these two things? Well, in order to change the energy of something, you've got to do both of these. Okay, Tyler's desk right now isn't moving. Okay, it's got zero energy. If I want to change its energy, then I need to give it energy. It needs to have energy that it doesn't have right now. Well, how does it get energy? It gets energy by something or somebody pushing it. You need to apply a force. Okay, there's F, the force. You don't push that desk, or something doesn't push that desk, and it's never going to move. And if it never moves, it's never going to gain or lose energy. It's always going to keep the same energy as it has right now. Therefore, no work will ever be done on it. You need a force. But it's not enough to apply a force. We said at the beginning of this unit, way back, okay, way back before our forces test, but still part of this unit, we said that a force can do two things. It can accelerate the object, or it can deform the object. Okay, if I just apply a force and deform the object, I'm not doing any work on it, because the desk isn't changing energy still, right? I'm changing its shape, but not its energy. If I push the desk and it moves, now I'm changing its energy because now it's moving. So we need not only a force, because forces can cause bending as well, right? Or bending or change of shape as well. But we also need displacement, a force and displacement. So we say that W is equal to delta E, but we also say that W is equal to F times delta D, force times the displacement. And I have that little thing that's in italics there. The force and displacement must be parallel to each other. What do we do if they're not parallel to each other? Well, it says here that we have to find a component that is parallel to the displacement. There's a little bit of a shortcut, though. On your data sheet, the equation for work doesn't look exactly like this, F times D. What does it say? W is equal to F times D times, is it? Yeah, F times D times cosine theta. And what that cos theta does is effectively, somebody mentioned this before the break, effectively finds the x component of the force for me. So in other words, the component of the force, the part of the force that's in the same direction as the displacement. So let's say we've got a wagon that we're pulling. We go back to this example a lot because it's a perfect example that describes a lot of things here. The wagon's moving to the right. Okay, that's its velocity. Okay, that's what wagons do. They move along the ground. But we're pulling it up this way. Because I was just pulling my son in a wagon yesterday to 7-Eleven to get a Slurpee. Pulling the wagon this way. We're pulling it at an angle of, let's say, 40 degrees. We're pulling it at 40 degrees, but it's moving horizontally. I'm not going to pull it at 40 degrees if the wagon moves at 40 degrees. It's going to fly. It's going to fly up into the air, right? It moves horizontal, parallel to the ground. So what's the angle that I use here in my equation for the work if I was trying to find the work that I did? Whatever that force is times however far it moves times the angle 40 degrees. What about this one? What if I'm pulling a box up an incline like this, incline of 30 degrees, and I'm pulling it straight up the incline here? What's the angle that I'm pulling it at? 30 degrees. Which way does it move? 30 degrees, right? Moves up the incline. What angle do I use when I plug it into this equation in order to find work? F times D times cos theta. What theta do I use there? 30 degrees? Why wouldn't I use 30 degrees? That's my angle, right? What did we define the angle as? The angle between the way that it's pulled and the way that it moves. Which way is it pulled? 30 degrees. Which way does it move? 30 degrees. What's the angle that I use in there? Someone's got to get this. Zero. If I move it one way, because I apply a force that way, what does it matter that it's on a hill at an angle of 30 degrees? What matters is the angle between the way that I pull it or push it and the way that it moves. Does that make sense? The difference between this one having an angle of 45 degrees and this one having an angle of 0. Okay, we don't see that all that often, but it's important. When we do see it, we've got to be able to deal with the angle and know whether we're dealing with 0 or 45 degrees. All right, we did a question class here on Friday. We also assigned 4 questions on page 294 that went along with that. I'm not going to call you up and have a look at that because I realized at lunchtime today that I texted the homework and I texted it as page 284, not page 294. So it's get out of jail free if you just forgot to do it. Any issues with any of these 4 questions on page 294, please? Number 3. That's when we're finding the angle, so that's a little bit tougher. Yeah, for sure. Any others? Okay, it says a force of 640 newtons in number 3. Okay, a force of 640 newtons does 12,500 joules of work. W is equal to 12,500 joules with a displacement of 24 meters. Now, we're not told whether we're pulling it in the same direction that it's moving or not. In fact, we're trying to see if it is. If we find the angle when we calculate it is 0, then we must have been pulling it in the same direction as it moves. If we find that it's not 0, then we weren't pulling it in the same direction as it moves, like the wagon. So let's use the equation, the general form of the equation, F times D times cosine theta. And let's solve for theta. Let's get rid of the F and the D first. It becomes cosine theta is equal to W over F times D. Does that make sense? F and D are multiplied by cos theta, take it over by dividing. How do you get rid of the cosine now? How do you solve for theta in this whole thing? Yep. Yeah. Inverse cosine or the second function of the cosine. W over F times D. So we're going to say the inverse cosine. You can do that on your calculator. We'll show you in a second here. 12,500 over 640 times 24. Okay, let's do that on the calculator now. First of all, when you're dealing with an angle at all, we should just make sure that we're in degree mode. Okay, it says degree mode up there, so that's good. Let's say second function cos, inverse cos, bracket 12,500 divided by, let's use some brackets on the bottom as well so we can multiply those two numbers together. Bracket 640 times 24. End the bracket on the bottom, end the bracket on the top, equals 35.6 degrees. How many people got that? Kathleen, does that make sense? The big thing with that is the rearranging of it, right? Because it's involving a trig function instead of just regular variables. Good? Well, after we did that, guys, we did another example here, which was a little bit trickier. A little bit trickier. This one said the object gains 300 joules of kinetic energy as it's pushed this distance. What's the force? The big thing that we had to recognize here is that the change in kinetic energy is equal to W. So we had W. We have the distance. And we were asked to find the force there. F is equal to W over D. And we found that on Thursday, and I don't think we had too much trouble with that. A little bit trickier, simply because we weren't given the work, we were given the change in energy. But the work is the change in energy. All right, we had 3 worksheet questions as well. Worksheet number 3 on work, questions 1 to 3. I'll give you some answers for that one right now, and then we'll take a peek at any of those if we have to. Question number 1 on that worksheet was 45.0 joules. And the conversion of energy was from nothing. We had no energy. This toy had 0 energy to start with. to kinetic. So it was a conversion of nothing to kinetic. Well, where did the energy come from ultimately? It came from me, right? When I pushed the car, there was chemical potential energy in me converted to a kinetic in the car. But within the car itself, there was none, and ultimately we had kinetic at the end. Number 2, we get 83.3 newtons. And number 3, what's the answer to number 3? This is pretty much the same question. In number 2, it says 1,000 joules of work is done. In number 3, it says 1,000 joules of energy is gained. What's the difference there? Change in energy is work. It's the same question. It's phrased slightly different. It's exactly the same question. So the answer for number 3 is 83.3 as well. Okay, any of those 3 questions we need going over? I believe I do. I'll check here in a sec, Brian. Any questions among those 3? No? All right, perfect. All right, let's do another example then that's not in your book. You're going to have to copy down here. This one says a 1,200 kilogram car accelerates from rest to 90 kilometers per hour over a distance of 200 meters. Calculate the work required to do this and the net force required to do this. Well, let's write down some givens first of all. Okay, we know this is a work question. Let's write down some givens here. Our mass is 1,200 kilograms. What else do we have? 90 kilometers per hour. We don't want those kilometers per hour, right? We want meters per second, but we'll deal with that later. What is that, by the way? V what? V, VI, VF, delta V, what is it? It accelerates from rest 7 to 90 kilometers per hour. What's the 90? VF, yeah. Do we know what VI is, by the way? What is it? 0. It's at rest. Displacement is 200 meters. We're looking for the work, and we're looking for the force. Let's convert this to meters per second. 90 kilometers is 90,000 meters over 3,600 seconds, which is 25 meters per second. Okay, good. Now, usually when we want to find work, we do this. W is equal to F times D. But I got a problem here. I don't know what F is. I do know what D is. But I can't find W by multiplying F times D when I don't know what F is. Anybody have any ideas here? Maybe we should go to the second part of the question and find force. Force is equal to W over D. But I got a problem there as well. I don't know what work is. So what am I going to do? Force is also equal to mass times acceleration. That's not what I was going to do, but that's correct. Okay, don't write this down yet. Okay, we're gonna work through this. Okay, because Tara's got a good way to do this question. I'm going to show you that it is legitimate and that it would get you the right answer. But there's another way as well that I want to focus on today. Okay, F is equal to m times a, but we don't know what a is, right? And we're going to figure that out by saying probably VF squared equals VI squared plus 2AD. Right? Yeah, that works, right? That would work. But there's another way I want to do it. Work is equal to F times D, but it's also equal to what? The change in energy. That's the work energy theorem that we briefly addressed on Thursday, and then we talked about just a minute ago in a review as well. The work energy theorem, W is equal to delta E. The final minus the initial. What kind of energy do we have at the end of this problem? What does it got? Car speeds up. What does it have after it speeds up? What is it? Kinetic. It's moving, right? So the final energy, EF, is going to be 1F mvf squared. What kind of energy did the car have at the beginning? It's sitting there, right? Nothing. All right. W is equal to 1/2 mvf squared minus 0. 1/2 of 1,200 kilograms times 25 squared minus 0. Let's figure out what this is. So 0.5 times 1,200 times 25 squared minus 0. It's 37,500. No, 375,000. 3.8 times 10 to the 5 joules. We do it Tara's way. F is equal to m times a. Vf squared is equal to vi squared plus 2ed. Guess what we're going to get for W? 3.8 times 10 to the 5 joules. Okay, they're both legitimate methods. Use either one of them. This way tends to be a little bit quicker, though, I think, now that you've seen it, right? Is that okay? We're going to give you some questions to work on. And although Tara's way works, and I would never shut you down or mark that wrong on a test, okay, I want you to do it my way on this worksheet. Okay? Not because it's a better way, although I do think it's quicker, and I want you to be exposed to that. Okay? I want you to do it my way today only because I want you to become familiar with it. Okay? And then you can make your own choice come test time, which method you use. Okay? So what do I want you to do? The rest of worksheet number 3, the work worksheet, except for, at this point, question number 9. So I want you to go questions 4, 5, 6, 7, and 8. All right, everyone, request to do number 5 on worksheet number 3, your work worksheet. It says a 1.30 times 10 to the 3 kilogram car begins at rest and accelerates to a speed of 60 kilometers per hour over a distance of 200 meters. What's the net force? We did number 4 already, and we found the work done was 1.81 times 10 to the 5 joules. We did that by using the work energy theorem. We did that by saying, look, W is equal to delta E. And we know that delta E is the final energy minus the initial energy. This car begins at rest. It ends at a certain speed. Its final energy is therefore kinetic, 1/2 mv squared. Its initial energy is 0. We want to find the work, as we did in question number 4. Let's see, W is equal to 1/2 mvf squared. 1/2 times the mass times the final speed. 60 kilometers per hour works out to be what in meters per second? 60 times 1,000 divided by 3,600 worked out to be, who's got that value? I don't have it written down on my page. Somewhere in the range of, I don't know, 15, 16? What is it? 16.666? Okay, minus 0. When we do that math, it works out to be 1.81 times 10 to the 5 joules. So that's the answer to number 5. Sorry, to number 4, getting the work. Now we want to find the force. We already have the work. So let's say W is equal to F times D. Here's my work energy theorem, the definition of work really. And here's my equation that we learned, F times D. Now, we sometimes tack a cos theta on the end of it. When do we need the cos theta on the end of it? That's important if and only if there's an angle. Is there an angle in this question? There isn't. Presumably, the force is applied in the same direction the car is moving. So the angle is 0. Let's leave it as F times D. Let's rearrange it to solve for F. Take the D over by dividing. We get 1.81 times 10 to the 5 joules, and we divide that by the displacement given to us of 200 meters. That gives me 903 newtons. Is that okay? So, look, these are harder questions than we started off with on Thursday before the break. W is equal to F times D. Even tack a cos theta into there doesn't make it that much harder. Okay, now it's not as simple as F times D, although we did use that equation. Now we've got to remember that work energy theorem, that delta E, that 1/2 mvf squared minus 0. Okay. If that is, it has kinetic energy at the end and 0 at the beginning. Okay. There are some questions. I think the next question, number 6, is one of those questions where it's the other way around, right? It's stopping. The object is stopping as it hits the ball. Luis, was that the next question? I think number 6 is where the ball is stopping as it hits the wall. Let's take a look at that one as well while we're at it, okay? This one says a 4.30 times 10 to the minus 1 kilogram ball traveling at 130 hits a wall and comes to a stop. So instead of the car speeding up, the ball is slowing down, squishing itself 2.30 centimeters. What's the force of the wall acting on the ball in order to stop it? What's the force of the ball that's acting on the wall? Well, we'd like to say W is equal to F times D. My problem is I don't know what F is. I do know what D is. I don't know what F is, though, so I can't do that. Let's use the other thing that I have for work, my work energy theorem. W is equal to delta E. Final minus the initial. What kind of energy do we have when it stops? The ball isn't moving. It's done. The final kinetic energy of the ball is 0. The initial is 1/2 mv I squared. Mass here is 0.430, and the speed was 130 kilometers per hour. That worked out to be somewhere in the range of, I don't know, 29 meters per second. Who's got that number exactly? 36 thank you, Ryan. I was way off on that one. 36.111 meters per second. And then, of course, we square that. We do the math there. I think we end up getting a negative 1.22 times 10 to the 4. Ryan, is that what you got? 1.22 times 10 to the 4. Okay. So the force, one of the forces is neg 1.22 times 10 to the 4. Which one is that? Is that the force of the wall on the ball or the force of the ball on the wall? If the ball is moving to the right, which way does the wall have to push on the ball to stop it? If the ball is moving in the positive direction, then the force, sorry, that's work, right? We haven't solved for force yet. Okay? That's not Newton's, actually. That's joules, right? Is that right? Oh, sorry. Sorry, I skipped steps on my answer key. Ryan, what's the number there that you get there? 280? 280 joules? Okay, so now we're going to say W is equal to F times D. Solve for F. It's 280 over the displacement, which is 0.0230 meters, right? 2.3 centimeters. And that's negative 1.22, right? Times 10 to the 4. So I had the right answer. I just skipped a couple steps there. So the ball is moving to the right. The force of the wall acting on the ball is to the left. If the ball is moving in the positive direction, then the force has got to be a negative force. So that's the force of the wall acting on the ball, not the other way around. The second part of that question, what's the force of the ball acting on the wall? That's an easy question. If the wall pushes on the ball with neg 1.22, then the ball pushes on the wall with positive 1.22. That's Newton's third law, right? If object A applies a force on B, object B applies the equal and opposite force on object A. So one of them is positive, one of them is negative. That's okay? Almost the same question as we had, right? Except that this time the object was slowing down instead of speeding up. So instead of being 1 FmV squared minus 0, it was 0 minus 1 FmV squared. Questions 7 and 8. Questions 7 and 8 are a little bit trickier because they use elastic potential energy. I'm going to leave you with those. Okay, elastic potential energy. 7 and 8 are homework, guys. Let's take a look at number 9. I didn't assign this one yet. We're just going to do this one as a group here, okay? Calculate the work done on the object in the following graph. Well, that should be easy, right? Can you guys see that graph? It's not a very good black line, but you can see that it kind of intersects at negative 3. Yeah, it's not, I know it's not a good graph. Intersects at -3, so it looks like this. Okay, we'll redraw it here, okay? Okay, so it looks like this. Oh, where is this? What's this number right here? Can you guys see that? It's a 3. That's a 3. I know it's pretty hard to make out, but you guys can see the graph up on the board now. It's not to a perfect scale, but that's okay. You want to find the work here? Well, what are we going to do? The idea here, anytime we have work, a work problem, is that technically we can say W is equal to F times D, and W is equal to delta E. The only problem here is that F changes. F is changing from -3 up to +7. So which value do we use? That's a little bit tough to decide, right? In the end, what we do end up using is the average value. Okay, but that's not going to be the way we're going to tackle this question. Okay, we're going to throw this equation out the window because force is not a constant value. Anytime we have a force that's not a constant value, we probably don't want to use the equation. Remember this, 3 words. If you see an F versus D graph, force versus displacement, then I want you to think these 3 words. Area equals work. Area equals work. So what I want you to do is find the area of this graph, the area between the x-axis and the line. There's 2 shapes here. There's a triangle right here, and there's a triangle right here. The area of section 1 is 1/2 of the base, which is 3, times the height, which is 3. Goes down to -3. 1/2 of base times height is going to be 4.5 joules. The area of section 2 is also a triangle, 1/2 of base times height. We're going from 3 to 10 for the base here, so the base is going to be 7. The height goes from 0 to 7. 24.5. What do you think we're going to do with those 2 areas? I heard somebody say it. What is it? Add them. When we add 4.5 plus 24.5, we get 20. Why? Why do we get 20? Shouldn't it be 29? Why do we get 20 there? Jazzy, I saw almost like a look of some epiphany on your face there a second ago. Why is it 20? Yeah, why is the first one? Why should the first one be a negative 4.5? Yeah, does it? Yeah, yes, exactly. Because the force applied is negative. If the force applied is negative, you're taking energy away. This adds energy to the system. This takes energy away. This has got to be a negative. Okay, the rule of thumb is this. Look, if the triangle is below the x-axis, make it negative. If it's above, make it positive. Add them up. If you got 2 shapes above the x-axis, just make them both positive. 2 below, make them both negative. 1 above and 1 below, make the one that's below negative and the one that's above positive. Is that okay? I don't have more questions for you to work on that, but that's easy, right? If you want to make up a question on that, how hard is it to make up a force versus distance graph? Literally just draw a graph and make up some numbers and find the area. Okay, just a curiosity here. We're going to move on to the next little topic, which is closely related to work here. But before we do that, I want to do a little poll here. Is there anybody in this room that happens to live next door to somebody else in the room? Anybody next door neighbors in here? Yes? Who are your next door neighbors to? You guys are next door neighbors? Like literally next door? Okay, perfect. So, Quinn, it's April the 28th. April is Surprisingly, most people don't think of this, but April is the month of in Alberta where we get the most snow, actually. Statistically, we get more snow in April than we do in any other month. Everyone thinks it's spring, but really it's kind of the beginning of winter in Alberta. Quinn, April 28th, let's say on April 30th, it snows, and it snows a lot. Let's say we get 45 centimeters of snow. That's a lot of snow. We never get that much in Alberta, but let's pretend we do. School's canceled. It's a great day. Nobody has any school. Nobody can get out of their driveway. But Quinn's mom gets him up at 7 in the morning and says, listen, you got to get him shovel the driveway. Like, earn your keep around here. Your mom also asked you to get up and shovel the driveway at 7 a.m. You guys both go outside. Shovel your driveways. You both have identical driveways because you live in the same neighborhood and you live beside each other. So same length of driveway. Okay, same width of driveway. Okay, they both shovel the same amount of snow, right? Quinn shovels his driveway, or sorry, Spencer shovels her driveway in an hour. It's a lot of work, takes an hour. Quinn shovels his driveway, same amount of snow, in 3 hours. Who did more work? Quinn or Spencer? Who did more work? I heard somebody say it's equal. Somebody say that Quinn did more work because he worked longer. Anybody want to say that? Everyone's afraid to speak up here. Anybody want to say Spencer did more work because she did it quicker? So one person wants to say that they did the same amount of work. Wow, you guys are fence sitters if I ever saw a fence sitter. They did both do the same amount of work. On average, they both applied the same amount of force over the same distance. They both had to get rid of the same amount of snow. So although, maybe Quinn's shovel picked up half as much snow as Spencer's shovel, or maybe twice as much snow as Spencer's shovel, and therefore he had to apply more force on certain shovels. Other shovels were less force. So on average, it worked out to be the same amount of force, same amount of displacement, same amount of change in energy, the same amount of work. But Quinn did it in 1/3 the time of Spencer. If we're going to quantify that work, if we're going to quantify what they did, let's not do it in terms of work. Let's do it in terms of power. Okay, if I want to pay these people by the job, then I don't care who I hire because they both do the same amount of work and I'll pay them the same amount. But if I want to pay them by the hour, I don't want to quantify the amount of work that they did. Anybody can shovel that driveway. I want to quantify the amount of power that they had, how quickly they did the work. Does that make sense? So not work, but power. The rate at which work is done, how quickly the work is done. Now power, given by a capital P, not a lowercase p, a capital P. It's equal to work over the time, the rate at which work is done. Anything that's a rate has time on the bottom. So the rate at which work is done is work over time on the bottom. Anybody want to take a stab at what the units for power would be? How quickly the work is done? Dollars? No. Funny enough, that's not right. Let's go joules per second, right? Work is joules, seconds is time. What would the other set of units for work be? What would they be? What would they be? What would they be? No. What would they be? Watts. Very good. I told you what they'd be. I said, what would they be? 1 joule per second is a watt. Now, it's a little bit confusing here because the symbol for work is W. The symbol for watt is W. Work is in joules. Watts measures power, not energy. So it gets a little bit confusing, but usually it's okay. It's not so bad because of context. Here's the example problem that we want to do. We're going to take a look at a set of stairs here. You don't need to copy this down if you don't want to. because you're going to actually do it as opposed to write it down. You're going to run up the stairs as fast as you can. Well, you don't have to run as fast as you can. But if you want to compete, which if it was me, that's what I'd want to do is compete. You're going to run up the stairs and you're going to find the power output of your legs. You can compare the power output of your legs to the power output of somebody else's legs. Now, if you don't want to run up the stairs, that's okay, walk. Your power output will be less. That's okay. If you're not trying to win, that's okay. We want to find the power output of your legs. That should be easy, right? It's W over T. So what do we got to do here? We got to measure the time. That's easy enough. Use a stopwatch. Just time it with a stopwatch or an iPhone or whatever. Just use a timer. Okay? Do it yourself. Okay? We'll trust you that you didn't make up your time. Okay? Start it the instant you leave. Okay? Your foot leaves the ground. Stop it the instant both feet get to the top of the flight of stairs. Work. How are we going to find the work done in getting up those stairs? Well, work is equal to the change in energy. What kind of energy do I have at the top of the stairs? Yeah, potential. What kind of energy do I have before I start? 0. So the work in this case would simply be mgh. Final over the time. That makes sense? We need to measure the height of the stairs. That's easy. We'll use a tape measure to do that. We need to know what G is. That's easy. It's 9.81. We need to know roughly what your mass is. And we have to measure the time. Everybody's going to do that real quickly. Okay, once you're done that, you're going to come back in. You're going to plug in your numbers here, and you're going to find out what your power output is. I want you to make a guess, though, right now on your paper before you go out there. I want you to make a guess at what your power output is going to be in watts. It is more or less a guess because you don't really have any context for this. Is it going to be 6 joules or is it going to be 64 million joules? Make your guess. Sorry, not joules, but watts. Watts, yeah. Make your guess, write it down.